Welcome to our latest explainer. Today, we're taking on a journey that pretty much every student, parent, and teacher knows all too well. That exciting, but let's be honest, kind of intimidating leap from grade 4 to grade 5 math. You see, grade 5 is right around the time when math stops feeling like just simple arithmetic and starts looking like a whole new language. It can feel like a steep climb, but it really doesn't have to be. In this explainer, we're going to unlock a series of highly effective visual tools and strategies, straight from the curriculum, to demystify why math suddenly feels so much harder. And more importantly, we'll see exactly how to build a rock-solid bridge to mathematical success.
Now, if you've ever stared at a word problem and just thought, what on earth is this asking me? Hey, you are absolutely not alone. One of the biggest hurdles in this transition isn't actually the numbers at all, it's the words. Language so often just gets in the way of the math. Students struggle with reading comprehension, they might be missing some specific mathematical vocabulary, or they just have a really hard time translating a dense paragraph into a clean, simple equation. When kids start over-relying on just hunting for keywords instead of understanding the actual scenario, well, the whole thing can feel like an impossible puzzle. But don't worry, we've got a tool to fix exactly this.
So, here is our roadmap for today. We're going to conquer these concepts one by one to build up that math toolbox. We'll hit 1. Decoding math word problems. 2. Playing with number operations. 3. Seeing fractions and shapes. 4. Exploring symmetry and patterns. And 5. Mastering time and measurement. Let's do this. Section 1. Decoding math word problems. Okay, let's dive right into our first major challenge, making sense of those tricky word problems. The secret weapon here? It's something called a box diagram. You can think of a box diagram as a perfect visual translator. Instead of getting all tangled up in a long, confusing sentence, you just map the information directly into visual boxes. By simply looking at which boxes are filled with numbers and which boxes are left empty, you instantly know whether to use addition or subtraction to find that missing piece. It completely removes the guesswork. It literally turns a messy paragraph into a crystal clear visual math equation. Section 2. Playing with number operations. All right, now that we've decoded the words, let's pivot from theory over to play. Number operations aren't just a bunch of rigid rules on a page. They're incredibly flexible. Actually, if we just shift our perspective a bit, we can treat them like a game. And this setup right here brilliantly illustrates how we can gamify math. We see students playing a version of the NIM game right on the blackboard. They aren't just sitting there doing drills, they're actively strategizing, predicting, and using addition to outsmart their opponent. So, the rules are super simple, but the mathematical thinking required, it's pretty deep. Player 1 starts off by choosing either a 1 or a 2. Then, player 2 chooses a 1 or a 2 and adds it to the previous total. You just bounce back and forth, adding to a running total, and the first person to hit exactly 10 is the winner. Now, think about it for a second. What's the winning strategy here? If it's your turn, and the total is currently sitting at, say, 6, 7, or 8, what number do you pick to guarantee you can force your way to 10? This incredibly simple game builds amazing computational fluency and forward thinking. But you know, that flexibility isn't just for small numbers. Take a look at the number 156. We so often think there's only one right way to solve a math problem. But what if I challenged you to find 5 totally different ways to reach exactly 156? You could add a 2-digit and a 3-digit number. You could multiply a 3-digit number by a 1-digit number. You could even divide 2 completely different numbers to get there. The absolute beauty of math is realizing there are multiple, highly creative paths to reach the exact same destination. It's not about memorizing one single route. It's about knowing how to navigate the whole map. Section 3. Seeing fractions in shapes. Let's transition into what is without a doubt one of the biggest hurdles for students everywhere, visualizing the abstract world of fractions. This quote, pulled directly from the curriculum sources, perfectly captures the issue. Students many a times write fractions in the standard form, but may not understand the relevance of equal parts of a shape or a collection. Basically, this means a student might easily memorize how to write a 1 over a 4, but that doesn't necessarily mean they truly understand the physical, equal parts that fraction represents in the real world. Which leads us to a really common, totally understandable visual puzzle. Take a look at these two fractions, 1/4 and 1/2. Because 4 is a bigger number than 2, a student transitioning into grade 5 will very often guess that 1/4 must be greater than 1/2. The numbers are literally playing tricks on their intuition. So how do we fix this? Well, we have to step out of the numbers entirely and look at the shapes.
Now, what's really amazing here is how quickly we can shatter that misconception. By mapping the fractions out onto physical, equally sized rectangular boxes, the truth becomes totally obvious. Just look at the shaded regions. The visual proof clearly shows that 1/2 covers significantly more physical space than 1/4. When students can anchor those abstract fractions to tangible shapes, the confusion just melts away.
Section 4. Exploring symmetry and patterns. Now, let's bring that exact same visual logic into the realm of geometry as we explore symmetry and patterns. We're going to set up a quick, hands-on experiment to test a really cool concept called rotational symmetry. To do this, we'll use some physical manipulatives. Here's our starting point, just a simple cross made out of 2 ordinary ice cream sticks bound together. A very basic, everyday shape. Next, we identify the exact central axis. See that red dot right in the middle where the sticks intersect? I want you to keep your eyes fixed entirely on the overall shape of this cross as we kick off our experiment. Let's move to the next step and see how this builds. We begin to apply a little force and spin the sticks right around that central point. Notice how the arms are moving out of their original horizontal and vertical alignments. Keeping the momentum going, we stop halfway through our quarter turn. Now the shape looks like an X instead of a cross. It clearly looks different than when we started, right? But as we complete the rotation, boom! The visual proof is right in front of us. After a 90-degree turn, the shape locks right back into a position that looks perfectly identical to how it started. And that is the very definition of rotational symmetry. It's not just some boring definition in a textbook. It's a physical property you can actually see and feel by simply spinning a shape. Speaking of finding predictability in things, let's pause our narrative for just a second. I want to challenge you directly. Recognizing patterns isn't just for shapes, it's for logic too. Take a look at this sequence. 6A7, 7B6, 8C5. Can you decode this alphanumeric pattern on your own? Notice what's happening to the first number, then the letter, then the last number. The first digits count up, 6, 7, 8. The letters move alphabetically, A, B, C. And the last digits count down, 7, 6, 5. Decoding these kinds of patterns is the absolute foundation for algebraic thinking down the line. Section 5, Mastering Time and Measurement. Finally, let's bring this math journey all the way back to the real world. While students in this transition are going to be busy mastering physical space measurements, think perimeter and area, another massive part of applying math to our daily routines is mastering time. Part of this transition is becoming perfectly fluent in the 2 main ways we visualize time. On one side, we have digital clocks, which just hand us the exact digits. On the other, we have analog clocks, which actually require us to understand the geometry of a circle, using those sweeping second, minute, and hour hands. To translate between the two, a student has to firmly grasp the core relationship, that exactly 1 hour is equivalent to 60 minutes. But just knowing that fact? Not enough. They have to be able to actually feel it. So, the crucial point here is connecting this math to reality. Let's test your own sense of time estimation. How long do you think it practically takes to boil a pot of milk on the stove? What about filling up a large bucket of water from a standard tap? Are we talking closer to 1 minute, 5 minutes, or 15 minutes? When students start estimating times for simple household chores like this, minutes and hours stop being abstract numbers and start becoming a tangible, useful measure of their daily lives. I'll leave you with this final, provocative thought to take with you today. Take a really close look at your own daily routine. What meaningful activities can you accomplish in exactly 5 minutes? When you start breaking down your day like this, you quickly realize that fractions, patterns, perimeter, area, and time measurement aren't just concepts locked away inside a grade-4 or grade-5 classroom. They are alive, constantly moving, and shaping absolutely everything around you. Thanks so much for joining me on this explainer, and I hope you feel just a little more equipped to tackle the math in your everyday life.